Okay, good morning, good afternoon, good evening to the attendees of the Virtual Process 2020 show. I appreciate your time today to listen to my presentation. I will share my screen. Okay, so my name is Dan Hazen. I'm the General Manager for the Automation and Controls Division of MKS. And today I am going to be talking about how we leverage multivariate analytics to improve process monitoring and fault detection around discrete manufacturing applications. Um, so I'm presenting this on behalf of Andrew Wilson, my colleague. I have a set of agenda that I'll share with you here in a minute, and then at the end I have some contact information in case you would like to follow up with myself or Andrew Wilson. So, but before I start on the presentation, I wanted to give a quick introduction of MKS. I understand many of you listening to this presentation may not be aware of who MKS is. So MKS was founded in 1961. We have about 5,500 employees around the world, approximately a $2 to $2.5 billion company. We are largely in semiconductor manufacturing, as well as some other advanced manufacturing applications. We've been listed recently, the last couple of years, on Fortune 100's fastest growing company. And we have over 2,000 worldwide patents throughout the various business units within MKS. Now, in terms of the markets and applications that we play in, everything, as I mentioned, from semiconductor, so from deposition, etch, lithography, processes in semi, to various other applications and use cases spanning across more industrial applications, process packaging, all the way up to life and health science, medical device, pharmaceutical, and then into research and defense. And you can see some of the specific segments of those markets that we provide solutions into. In general, rather than trying to cover the broad MKS portfolio, I think the key things here is that we provide solutions in various spaces that deal with measuring data, measuring a process, monitoring delivery, so power delivery analysis, which is largely what we're going to talk about today, and then power and control. Okay, so that's a very quick, brief introduction to MKS Instruments. Now I would like to get into the meat of the presentation. So we have a very interesting topic here. I'm going to start off by providing a general overview of multivariate analysis and how MKS has implemented it to provide value to end users doing manufacturing, doing discrete processes. Also, we'll talk about a little bit about how this type of approach can be integrated with your tool or process, how subject matter expertise can be leveraged with a highly advanced, highly capable data modeling algorithm. And talking about the value of multivariate analysis and how it works and how it can provide benefits, I've got a handful of slides where I'll cover how it works, how multivariate works, why it's beneficial, especially in terms of a real-time monitoring and fault detection perspective. And then also I'll cover a little bit about how do we go about building good multivariate models. And then I have a couple case studies and a list of applications where this type of approach has been deployed in. So at the end of the day, the main message that I want to get across to kind of, start with the conclusion or the summary, really what we're talking about here is a method and approach that would allow a manufacturer to be able to convert process data to insight and then to action, and to be able to do that in a highly automated way. And at the end of the day, that's kind of the key message to get across. That's what our solution is enabling. I think there's also some learnings to be taken from this presentation to maybe integrate into an existing process monitoring system that you may have in place today. So in terms of what can we do with that, or what sort of benefit can we obtain from that? The biggest use case that I see this approach used in is in the real-time quality prediction of the process output. And so, if I think about this in terms of a packaging application, or where you're manufacturing, preforms of a plastic bottle of a Pepsi or Coke bottle, where this solution can be leveraged is to be able to do accurate real-time predictions of the product that's being manufactured from that product line based purely on the process data using multivariate analysis. What I like to say is, if you can model it, if you can build a model where you can correlate the data to the quality, then you don't have to measure it. And I'll show you kind of how that works and what that looks like in terms of this type of approach. Another side benefit, and I have a case there, I have an example on this, is optimizing preventative maintenance scheduling. I'll talk a little bit about exactly what that looks like and what that means. Also, characterizing various raw inputs. And so that could be your raw material. It could be other inputs into the process. It could be the environment around the process, around the tool, around the machine. Also, being able to reduce downtime. So, by using a multivariate analysis, we can essentially incorporate lots of different sensors, lots of different process variables, and still very quickly pinpoint down to the root cause as to why the process may have deviated out of control. And then if I add all these things up, I think at the end of the day, what it amounts to is improved yield and reduced scrap, and then, all the cost benefits associated with that. So from a high level, what we're going to be talking about is a platform or solution that combines data-driven multivariate modeling while also enabling the incorporation of subject matter experts, because that's extremely important. I see some approaches that rely purely on a data-driven approach, and then I see other approaches that are more physics or subject matter expertise driven. And the beauty of what I'm going to talk about today is that it really combines the best of both worlds. So the idea with the multivariate analysis is that you have to kind of establish a model that represents your process, and then you can run that model in real time to do accept and reject control, and to the point to where future process data is compared to that model, and then accept and reject decisions are made. So if I take a look at what that looks like in terms of an actual process and some of the components around it, so we have a platform called the SenseLink QM that will incorporate into a process or machine or tool where various sensors are being sent to our device, and then from those sensors we're calculating some key attributes and process variables. And I'll talk about that a little bit later on in terms of what sort of capabilities there are. But obviously you've got to collect data from the process. That's kind of step one. The second step is you need to be able to visualize your process. So configure and visualize. And so we have a web-based user interface. So the idea is the unit, the SenseLink QM product would reside on a machine in an electrical cabinet or something like that. Signals are wired, and then we have the system can be wired into your network. And then using an IP address, you can access the unit from the network, and you can configure, set up other process variables, visualize the process. And you'll see kind of this radar screen throughout the presentation that represents the summary of the multivariate analysis. Also, we have the MVDA engine. So MVDA stands for Multivariate Data Analysis. You'll see this abbreviated as MVDA and MVA kind of throughout the slides. But the idea is we have an embedded multivariate analysis engine that resides and runs in real time on the device. And the user interface is displaying the output of that multivariate analysis. Also, we have, as the unit is networked within your facility, within your firewall, you have the ability to automate the exporting of process data to a server, a PC, a database on the network, so that you have access to data 24/7 forever, basically. And then lastly, in addition to performing real-time accept and reject decisions, the other important aspect is to ensure that you can actually remove the defective product from the manufacturing line. So I talked earlier about Pepsi bottles where you're maybe making little vials or preforms, and you can be manufacturing 100 of those every 5 seconds. And it's important to ensure you have an automated part containment strategy and system in place to be able to remove suspect parts from the manufacturing line. So the system here has the ability to auto send an output to a robot, a converter, a conveyor belt, a diverter, another PLC to be able to perform some sort of reject activity. So from a high level, this is what the system, the solution is doing. This is kind of the methodology that I'm going to continue to talk through in the rest of the slides. Okay, so in terms of how this can be integrated with your process and tool, there's two main approaches really. And the first approach at the top here is we have a number of drivers that allow our system to be interfaced over Ethernet to a PLC, a programmable logic controller, which is likely how most of you are controlling your process. So you likely have some sort of PLC. Two of the most frequently used or frequently interfaced to our solution is an Allen Bradley and a Siemens PLC. And so if you have an Allen Bradley or a Siemens PLC or a Rockwell PLC, then we likely have an interface so that all you need is to connect an Ethernet cable between our system and then the PLC, and then we can pull the data directly from the PLC to do data analysis. The other approach is that we have off-the-shelf I/O modules or I/O slices. So if you have 40 analog and digital sensors on your machine, then you can incorporate our I/O modules to be able to connect the sensors on the tool directly into the I/O modules on our unit. And so one of the most commonly used processes is injection molding, and typically most of our injection molding applications just use the standard I/O modules, and then the sensors will interface directly into our blocks. And here is just a list of the various I/O modules available based on the different sensors that you have that you want to incorporate. Basically, it's flexible. It's virtually unlimited. So whether you have temperature, thermocouples, RTDs, pressure, position, velocity, anything literally can be interfaced to our system using one of these off-the-shelf I/O modules. Okay, so the next question, and this follows the connection of the sensors or the interfacing of the sensors, but the next question is, okay, what do we do with that sensor data? Typically, we are collecting that data at 10 millisecond intervals or even faster. And so for every single sensor that we are incorporating into our system, if we are running a 30-second cycle time process, we could have thousands of data points for every single sensor that we've incorporated. And so what we can do is we can provide the ability for an engineer or a subject matter expert to be able to determine what are the important attributes of the curve that I want to collect. I want to calculate and collect that I know are going to be important to my process. And so, most any process engineer would be able to look at a pressure curve or a temperature curve from a process and just know by looking at it, what are the various attributes of that curve we know are important, we know impact the quality of our product. And then through the user interface, we can, or a process engineer can configure various attributes or various variables that reflect the important attributes of that curve. And so essentially what that allows us to do is it allows us to take 10,000 data points from one sensor and convert that to a handful of specific process variables. And if we're talking about 10 sensors or 100 sensors, that can significantly simplify the data analysis that we're doing, and it can also shorten the computational time as well. So if I break that down into a graph and I show you specifically what this means, this is a pressure curve, again, from an injection molding process, and this is what a standard injection pressure curve would look like. What we can do through the user interface is we can segment this process out into various process steps. So I may have, I've got two major process steps, and then I've got step A and step B, and then I've got a definitive start and stop for each event. And so what I would do is I would configure those events in the configuration of my system. And then what I would do is I can say, okay, during step A or process A, I want to calculate a certain set of attributes from the curve, from the pressure curve. And so, for example, one of those might be the slope of this pressure curve. So I know it's important that I characterize the slope of this curve, and so I do a derivative of the pressure. And then I say, okay, well, it's also important that I understand what the maximum pressure that was observed during the process was, and so I capture a maximum point during that pressure. And then maybe the last thing that I need to measure in order to really characterize the entire shape of that curve during step A is an area under the curve, or an integral. And so then I apply an integral of that pressure curve during step A. And then I go into the next phase, or the next step of the process, and I say, okay, what are the important attributes during this next step, B? And you can see it's very different behavior and very different types of things that we're going to be measuring. It's more of a steady state type of behavior here in step B. And so, okay, maybe still the integral would be important, but maybe the maximum is not quite as important. Instead of a maximum, I want to do an average pressure during step B, and so I can very quickly, I can add pressure, and so that's just to give you kind of a feel for how this can be done. And keep in mind, this is done within just a few clicks of a button. Within 10 seconds, I can create each individual process variable here. But so, for example, from one sensor of pressure, I am showing how we are creating 1, 2, 3, 4 different variables, process variables, what we call virtuals, within the system. And those 4 or 5 process variables are pretty much characterizing what this entire curve looks like. So we're essentially summarizing, potentially tens of thousands of data points down to these 4 or 5 most critical attributes or process variables. And then this is kind of just showing some of the mathematical functions that are available to be able to create those variables. In general, I think there's probably 15 different math functions. There's standard deviation, there's some filters, and then you can see max, average, derivatives, things like that. Okay, so the next is to talk about multivariate analysis. When you hear multivariate analysis, what you can kind of think is that the multivariate analysis is an incredibly accurate way to capture the unique specific thumbprint or signature of every single individual cycle that runs on your machine. Every single cycle has a different process that was used to produce that product or a number of products. And so multivariate is extremely powerful in terms of characterizing that signature and that pattern and that process. And so the way that it is so effective at establishing that thumbprint of the process is largely based on how multivariate assesses and characterizes the relationships and the correlation structure that exist within your process and within all the individual process variables in your process. So the more dependencies, the more correlation that you have between all the different parameters in your process, the much more powerful multivariate analysis is going to be, and the much more value it's going to provide you as a manufacturer. So what that looks like in terms of fault detection is, if you think about the standard SPC approach that you probably have used or do currently use, that most manufacturers use, you typically define an upper and lower boundary around a handful of process variables that you know to be important to your process. And so what that looks like is you have an upper limit, you have a lower limit. I'm showing a temperature variable here, and then I have a pressure variable. I have upper here and I have lower here. And that gives me this box shape. And this is the shape that represents my SPC approach. If I go above and below or outside of the box, then I'm going to reject and determine my process to be out of control. Now, if I have two variables that are completely independent of each other, then this type of approach will work just as effective as any multivariate approach out there. However, as soon as I have two variables that are dependent and correlated to each other, the process space has now changed. And what the multivariate analysis is doing is it's capturing the new process window that considers the relationship between temperature and pressure. At the end of the day, this is how multivariate analysis is leveraged in a fault detection application or use case. It establishes a much more accurate process window around the variables in your process. And so in this specific example, the correlation that exists between temperature and pressure is if I have a high temperature, I should have a low pressure. And if I have a low temperature, I should have a high pressure. And if for some reason I have a low temperature and a low pressure, I have a correlation break between those two process variables. And that is many times where the defects occur. And so, we've done numerous studies where we kind of compare a univariate SPC approach to a multivariate SPC approach, and the results are astounding and quite powerful. And with the univariate SPC approach, you oftentimes have to set your limits very tight, but then you cannot build in the normal day-to-day, week-to-week variability in the process or from the raw material, and you end up having to move your limits up and down, whereas the multivariate analysis allows you to capture kind of a wide processing space while still considering the correlation and the relationship between the variables in the process. So this is extremely important, and this is really the value of leveraging multivariate to do better real-time quality prediction. So whether you're using an MKS solution or another system, this is really the power and the value that can be provided in terms of fault detection. So the one other thing that this allows is for the ability to do real-time virtual metrology. So, I'll go back again to the preform example where you're manufacturing maybe 100 preforms at one time, and there could be some critical dimensions of the preform. Maybe it's a height, maybe it's the thickness, and you want to be able to predict those metrics in real time. And so if we can establish a multivariate model that can correlate the process data to those specific dimensions, then we can do real-time predictions of those dimensions, of that length, of that height, of that thickness, without actually having to continuously measure the product. And so once we establish a strong correlation structure and strong correlation between the data and the metrics, then we can do real-time predictions, and we can establish accept and reject criteria based on those predicted dimensions. So this is an extremely powerful tool to be able to release product based on certain, critical dimension tolerances that you likely have. Okay, kind of the last step here is to talk about how you actually go about establishing that window. And so, you saw the radar screen before. I'll show it in a case study. But the multivariate analysis is really only as good as how you build the model, or the data that goes into building the model, or as you might call the training data set. So the question is, how do we build this training data set? One approach might be to collect historical data over time and build a model from that. The challenges or the issues there are that you may have to collect months worth of data before you have enough variability in your process so that the multivariate understands what is the normal accepted variation in your process between all the different process parameters. So this is extremely important. We've got some white papers published on our website that you can look at as well. But essentially, the way that we go about building this process space, or the way that we go about feeding data to the multivariate analysis so that we can build a good, robust model, is using a design of experiments approach. so DOE. And some of you may be familiar with DOE. You may be using it today to be able to optimize existing processes and tools. Your standard, the standard reasoning for using a design of experiments is for process optimization. And we are using it a little bit different. We are using it not necessarily to optimize a process, but to establish a multivariate process space or model. And so, a couple things that this does for us. One is it teaches the system the process window. It induces process variability. It induces good process variability. We all know that your process can likely run with multiple different conditions. You can modify the turn knobs and change settings in various regions, still make 100% good product. We want to make sure that any fault detection system that we implement allows for some level of maneuvering the process through different regions that are all acceptable. And the multivariate analysis needs to understand, okay, if I change my temperature, how does the rest of the process respond to that change? And so, so that's a very important aspect of the design of experiments. The other important aspect is that it can be done in a very controlled environment, in a very short time period as well. So we, most of the time, can come in and run a design of experiments in a few hours on a process to be able to establish a model. And the other thing that makes that useful is that we can assess the quality of all the product that was produced during that design of experiments. So this is a common example of the DOE that we typically use. It's a resolution 3 partial fractional factorial design. Basically, it's a partial design, and meaning it does not cover every single combination of factors. It's not a full factorial design. In terms of using this for optimization, there are limitations in using a partial design. You're covering partials of your process space, but we can cover a large portion of the overall process space. And so in this case here, what I'm showing is we have 9 factors, basically 9 knobs or process settings that we're changing through the design, and then we have 9 runs. So if you have, for example, a 30-second cycle time, we might run 10 cycles per run, and so you're talking about 90 cycles. And so most of the time, so with those conditions, this is a 3 to 4 hour DOE that we can run and establish a multivariate model. So it's really not too bad in terms of the value that you can get from this. So to show you what this looks like, this is one example from an injection molding application where the user would basically start up their machine every day, and after X number of time, maybe 10 minutes, they would start collecting samples. And for whatever reason, on this specific day, they started the machine up like normal, but there was they were making defects every 5 minutes. And what had happened was the heater bands in the process hadn't reached steady state, hadn't reached equilibrium, and the effect on that was causing defects to occur. And you can kind of see it almost like this flower shape on the radar screen that basically represents the overall process. But over time, what you're seeing is that the temperatures are reaching steady state, and then over time, the manufacturer made good product, and the system started to accept everything. Another interesting example is more on the lines of preventative maintenance. And so this is a welding application where there's a material, that orange material there was a die coming down and welding of a plastic material. And you can see that orange material, this is a new one, this is a used one, and you can see the indentation of the die coming down. And that had a drastic impact on the process. And when I look at one of our multivariate metrics, I can see as the multivariate metric is drifting up, and I changed that nest material, that welding material, then all of a sudden my process became optimized, and then I can see over time the impact of that wear getting worse and worse over time. And so essentially what you can do is you can establish a threshold on your multivariate metric that determines when a maintenance needs to be performed. And so it's a much more accurate method to schedule your maintenance, as opposed to just using a pure time-based maintenance, instead of saying every 2 months I'm going to do this maintenance. So it gets a lot more value out of your existing assets. And so this is just a list of some of the applications and use cases where we've deployed this methodology in. Everything from plastics manufacturing applications, injection molding, blow molding, extrusion welding, tablet compression. We've done some spectral analysis work, form, fill, and seal, even coatings, paint coatings, assembly operations. So I think the key is, in general, it works very well in discrete processes where you have definitive start and stop and a product that is produced. And so we've seen a lot of success in those types of use cases and applications. So with that, I think I'm about out of time. I appreciate everyone's time. I hope this was an interesting presentation. I hope you learned something. I hope, if you're doing some process control and monitoring today, that there's something that you can take from this and potentially incorporate it and improve what you're doing today. That would be fantastic. Here's my contact information. I've also copied Andrew's contact information, and I provided a link to the website of the platform that we talked about today. Otherwise, again, appreciate everyone's time, and I look forward to having a discussion with anyone that might have questions or want to have further discussion. All right, thanks for your time. Enjoy the rest of your evening.